Thanks for what I assume was a very nice introduction, and also for inviting me here to give the seminar. I'm going to be surveying an area of quantum algorithms, that specifically those that use random walks to design a quantum search algorithm. So Grover's search algorithm, which I think Fred lectured about today, is a special case of this kind of algorithm. Like Grover's algorithm, these quantum walk search algorithms in general are limited in that they can only give square root speedups. However, they also share the advantage that it's very easy to design algorithms of this type. Essentially, you just need to design a classical random walk algorithm of a particular form, and then you can sort of recompile it into a faster quantum algorithm. And because of this, there are quite a number of algorithms designed this way, including for combinatorial problems like element distinctness and subset sum, but also for cryptanalytic attacks on code-based cryptography and many other examples. In the past couple of years, there have been some new results in this area, so I thought it might be useful to highlight some of them. In particular, until recently, there were several distinct frameworks for quantum walk search, and I'm going to survey these, along with some examples of how to apply them. And then I'm going to describe a newer framework that unifies all of these, the previous existing frameworks. And this talk is partly based on joint work with Andres Sambinas, Andras Kilian, and Marcin Kokainis, as well as Simon Appers and Andras Kilian. So here's a map of Paris, which I used to visit often as a student. And I like to get around on foot, but it wasn't always easy to find my way around, especially because back then, as a student visiting from Canada, I never had mobile internet. And I somehow never managed to stay at the same hotel twice. I guess because most of the hotels are small, they just have a few rooms and they fill up fast. And I would usually just book whatever I could get cheaply 2 weeks in advance. So finding my way back to my hotel was often somewhat of an adventure. So not having the plan of the city in my head, one thing that I could always do is walk in a random direction. And this is a strategy that I encourage you to try the next time you're lost in any city, because you're guaranteed to eventually get back to your hotel this way. Every time you get to an intersection, you just take a random direction and you will eventually find your hotel, as long as you recognize it when you get there, which of course is another issue. The technical term for this kind of process is a drunkard's walk. And this is not always the most efficient way of finding something, of course, but sometimes random wandering is actually the best way we know how. And in fact, many classical algorithms are based on this kind of idea. As an example, suppose we have a formula phi, so its input is a binary string, and suppose it's a product of some number of clauses, or some simpler formulas that each depend only on a small number of bits to the input. So each of these xi's is a 0 or 1. And your goal is to find a string of bits x such that phi of x equals 1. It's not really clear how to solve this problem, so what you might do is just try a random string, like this one. Now, if phi of x is 1, we're done, so suppose it's not. And now you need to try another random string. But you could get a new string by just changing x slightly. So for example, you could just flip 1 bit, that gives you a new x to try. And this also might make it easier to compute phi of x because you only have to recompute the clauses that depend on the bit that you flipped. And it might take a very long time, but if you keep repeating this process, eventually you will find a satisfying assignment if there is one. Many algorithms have this structure, and abstractly we view them as a random walk on a graph, where the vertices of the graph represent all of the candidate solutions to the problem that we're trying to solve. So in this example, the vertices of the graph would be all of the binary strings of the appropriate length for the formula phi. And there's an edge between a pair of vertices if we want to consider a transition between those two solutions in one step of our algorithm. So in this example, two vertices have an edge between them if they represent strings that are the same, except they differ in one single bit. Then a random walk search algorithm works by starting from a random vertex and moving along this graph randomly until it finally lands on a solution, or what we call a marked vertex. The reason that these types of algorithms are interesting to quantum algorithms designers is that often, if the algorithm is structured just right, we can turn such a classical algorithm into a faster quantum algorithm. I'm going to describe several ways of doing this, and then I will describe a new method that unifies all the previous ones. So I'll start by introducing several different frameworks. But first, what do I mean by a framework? Well, Grover's search, or more generally, amplitude amplification, is an example of what I mean by a framework. And it's actually a special case of the other frameworks I will mention. It's quite simple, and well, I think that you've just all just seen it. So we'll start with this to really see what I mean. So consider a randomized classical algorithm that solves a problem by brute force. What that means is that the algorithm just keeps sampling potential solutions U and then checking if they're marked. Where by marked, we mean it's a solution to whatever problem we're trying to solve. It's the kind of thing that we're looking for. And then our algorithm just repeats this sum number 1 over epsilon times. For example, remember in the problem of finding a satisfying assignment for a formula, then U would be an n-bit string, and we would check if it's marked by evaluating the formula on it. If the probability that a sampled candidate is marked is 1 over epsilon, is epsilon, then we need to repeat this about 1 over epsilon times before we can find a solution with high probability. Of course, this algorithm is only a kind of meta algorithm. To actually implement this, we need some subroutines that do all of these things. So in particular, we need some subroutine that samples a candidate U, and how that's implemented will depend on what our search space is. And of course, we also need a subroutine to check if a candidate U is a solution or if it's marked. And how that's implemented will depend on the search problem that we're trying to solve. So back to the formula example, in that case, sampling an n-bit string uniformly at random should be pretty easy. And checking by evaluating the formula should also be rather straightforward, but of course, this could incur some cost. So generally, if we have such subroutines for a particular problem, and their costs are S and C respectively, then we can solve the search problem in question with complexity 1 over epsilon times S plus C. So this is an extremely simple and straightforward classical algorithm. So why is it interesting to us as quantum algorithms designers? Well, because we know that if we design such a classical algorithm, we can recompile it into a quantum algorithm that solves the same search problem, but whose complexity is better. Specifically, we get a square root over the number of repetitions 1 over epsilon. Anyway, this is what I mean by a framework. It's a way of taking a certain form of classical algorithm and recompiling it into a faster quantum algorithm. And I'm confident in saying that this is the most widely applied quantum algorithmic technique there is. And this is partly because it's so easy to use, but also because for so many problems, the best classical algorithm does have some step that looks like this. And using this technique, you can speed up at least that step. So now that we are clear on what a framework is, now I want to talk about a framework that's a generalization of this framework and based on a random walk. So we start with a classical algorithm that's based on a random walk P on a graph, where P is represented by a transition matrix indexed by vertices, and the UV entry of P represents the probability that a walker at U will move to V. Some of the vertices in the graph are marked, shown in red here. That means that they correspond to some sort of problem solution, something that we're looking for. So our algorithm will start by sampling a vertex according to the stationary distribution of P, which I'm denoting pi. And if you don't know what a stationary distribution is, don't worry. For a random walk on a graph, it's just a distribution over the vertices of the graph proportional to the degree of each vertex. But it's not so important to remember that for this talk. More importantly, pi is the limiting distribution of P, meaning that a walker will always converge towards the distribution pi after enough steps. So our algorithm starts by sampling according to pi. So we're going to need some subroutine that actually would implement that sampling. And next, our algorithm takes a step of the walk, meaning that it's going to, using some subroutine that will have to be specified, sample from a neighbor of whatever the current vertex is. And then the algorithm will check if the current vertex is marked using some subroutine that will have to be implemented. And then the algorithm will repeat this some sufficient number of times. So importantly, how many times does the algorithm have to repeat this process of moving to a new vertex and checking if it's marked before we can expect to find a marked vertex? Well, this quantity h is what's called the hitting time. This depends on the graph that we're walking on, and it also depends on which vertices of that graph are marked. And it's the expected number of steps a walker needs to take starting from the stationary distribution before she can expect to find a marked vertex. In other words, it's the expected number of steps before this classical algorithm finds a marked vertex. And although it's the expected number of steps, it also turns out that if we repeat this h times, or at least some constant multiple of h times, then we will find a marked vertex with high probability. So again, this is again some kind of meta algorithm, and to actually implement it to solve a specific problem, we would need to be able to, implement these three subroutines that I've listed here. So we need to be able to sample, take a step of the walk, and check if a vertex is marked. But then if we have such subroutines and we analyze their complexities as S, U, and C, then the complexity of this classical algorithm is given by this expression here. And well, the hitting time framework tells us that given such a classical random walk algorithm, we can recompile it into a quantum algorithm with this better complexity, where now we have a square root over h. I mentioned that this is a generalization of amplitude amplification, and that's because if the random walk is on a complete graph, so every vertex is connected to every other vertex, then each step of the walk is just sampling a uniform random vertex. So the update and sampling steps are the same. In that case, it's not difficult to see that the hitting time is about 1 over epsilon, where epsilon is the probability a sample vertex is marked. This framework, I think, has gotten relatively less use than it deserves. And I think one reason is that until recently, this framework had the drawback that it would give a quantum algorithm that wouldn't actually find a marked vertex, but would rather distinguish between the case that there is a marked vertex and that there is not a marked vertex. So the classical algorithm, of course, solves both problems. The classical algorithm can tell you if there is a marked vertex, but it does so by finding one naturally. Whereas there was this sort of strange situation where we had this quantum algorithm with this better complexity, but it wouldn't find a marked vertex, it would just detect one. And this was kind of an annoying open problem for quite a while until finally in 2019, we figured out how to get a quantum algorithm that actually finds a marked vertex in this complexity here, as one would expect. And I think this change makes this framework potentially much more useful to apply. So let's look at an example of an application. The problem we're going to solve is element distinctness. And in this problem, the input is a list of integers, and we want to find 2 of them that are the same. Or if we can't, then we will conclude that they're all distinct. So we want to find a pair I and j that are distinct such that xi equals xj. The algorithm we're going to see actually predates the framework. It was designed without the use of the framework, and then the framework came later, actually based on this algorithm. But well, the algorithm is much more easily described within the framework. So since we just have to design a classical random walk algorithm, so that's what we're going to see. To design this kind of classical random walk algorithm from which we can get a quantum algorithm, we first need to specify the graph we're going to walk on. So the vertices of this graph will be sets of R of the integers in our input. And 2 of these sets will have an edge between them if they overlap in all but one element. So that means that what our random walk does is at every step, it randomly replaces one of the elements in the set with a new element. Finally, since we're ultimately looking for a collision or a pair of elements that are the same, we will say that a vertex is marked if it contains a collision. So if it contains 2 of the same integer. So for example, this last vertex shown here has 2 purple balls. And so this would be marked. It has sort of 2 of the same integer. So this yields a classical algorithm where we start by sampling a uniform random set of R of the inputs. This requires time approximately R, let's say, and neglecting some log factors. We would need to sort the inputs into some useful data structure. And then when we take a step of the walk, that is we update, we just need to remove one of the things in the set and replace it with another. And well, we'll call this cost constant. Again, we're neglecting the log factors of removing and inserting things from whatever nice data structure we use. And then assuming that we are storing things in some sort of like sorted data structure, it should be pretty easy to detect when there's a collision, when two things are the same. So we'll also call the checking cost 1. And then finally, to finish the analysis of this algorithm, we need an upper bound on the hitting time. And I claim that R times n squared over R squared is an upper bound. And that's because after approximately R steps, you've probably mostly refreshed all of the things in the set. So you pretty much have a fresh random sample of R uniform random integers. And assuming there's at least one collision in the input, the probability that both elements of this collision are in a random set of R things is R squared over n squared. So if you repeat this process, n squared over R squared times, then you will likely find a collision. So this gives us an upper bound on the hitting time of R times n squared over R squared. Yeah, now these are all of the things we need to analyze the complexity of this algorithm. This is actually not a very interesting classical algorithm. If you want to use as little time as possible, then you should just take R to be n, and then your algorithm basically just sorts the whole input to find a collision. And this also happens to be optimal, at least in terms of time, for a classical algorithm. However, when we use the framework to get a quantum algorithm, we have a square root over h, so we get this better complexity. And now the optimal value of R is n to the 2/3, and in that case, we get a quantum algorithm that finds a collision in n to the 2/3 steps. And that happens to be optimal for a quantum algorithm, and it's better than would be possible for a classical algorithm. A classical algorithm requires at least n steps. So using the framework, we were able to design this algorithm just by reasoning about a classical random walk algorithm and then kind of applying this very useful tool. So this was the hitting time framework. Now the next framework I want to mention is a generalization of this framework. And it's based on a more general classical algorithm that you've already probably thought of, which is that we're just going to start in an arbitrary distribution sigma instead of restricting ourselves to the special stationary distribution of the walk. And this changes a couple of things. First, sampling from sigma might have a different algorithmic cost than sampling from pi. In general, the cost of sampling will depend on sigma, which, sigma is now a parameter of the algorithm. So we write the cost of sampling as S sub sigma. And then second, the hitting time H is defined as the number of steps needed to find a marked vertex when the walker starts in the stationary distribution. So if we start in a different distribution, the number of steps we need would also change. Now we could define some new quantity that's the hitting time starting from sigma. That is, like, we could define a new quantity that's sort of the number of steps that this classical algorithm needs. But actually, in this case, our quantum algorithm will actually not depend on this quantity. Instead, it turns out that we can compile this kind of algorithm into a quantum algorithm whose complexity depends on the square root of some quantity called C sigma, where C sigma is not the number of steps the classical algorithm has to take. So it's something different. So what is this quantity C sigma? Again, it's not the number of steps the classical algorithm takes. And it's actually kind of technical, so I don't even want to give a precise definition in general because it's a little bit too technical. But I will say it's related to the resistance of the graph when a potential from sigma to the marked set is applied. And that's why this framework is called the electric network framework. If that doesn't make sense to you, then please disregard. That's no problem. More importantly, I want to give some special cases where we understand what C sigma is that I think gives some important intuition. So in some special cases, what is C sigma? First of all, when sigma is pi, C sigma is actually just H, the hitting time. And in that case, we just recover the hitting time framework. A second important example, when sigma is a distribution that's supported only on a single vertex S, and the marked set, usually denoted by capital M, contains only a single vertex, small m, Then C sigma is actually the commute time from S to M, which is the expected number of steps a walker needs starting from S to reach M and then return to S again. And note that this is, in this case, C sigma is an upper bound on the number of steps a classical algorithm would need, right? A classical algorithm starting from S needs to reach M, but it doesn't need to return to S again. So the quantum algorithm might get a square root speed up in the number of steps in that case, but it also might get less of a speed up. And in more general cases, we actually don't have such a nice interpretation of what this quantity C sigma means. I mentioned that the hitting time framework suffered from the drawback that the quantum algorithm it produced could only distinguish between marked vertices and no marked vertices. It couldn't actually find one until this problem was solved recently. And similarly, this generalization suffered from a similar drawback until even more recently when my co-authors and I solved the problem here as well. So here we also get a quantum algorithm that finds a marked vertex, which is also probably what you would have expected anyway. So now let's see an example of an application where it's actually very useful to be able to start in a distribution that is not the stationary distribution. Imagine you have a tree with some of the leaves marked. For example, we can consider backtracking algorithms. So some of the best practical types of algorithms for constraint satisfaction problems explore a tree, and this tree is obtained by setting variables to a particular value. So one thing we could do is we could fix a variable at each level of the tree, and then we always have two choices of how to set the variable. So we could set x1 to be either 0 or 1, and then we could set x2 to be either 0 or 1, and then we could set x3, etc. And then each leaf corresponds to a complete assignment of the variables. And we say a leaf is marked if that assignment satisfies the formula. So for example, if phi of 0, 1, 0 is 1, if 0, 1, 0 is a satisfying assignment, then this leaf would be marked because we obtain this leaf by setting the variables to 0 and then 1 and then 0. So one way to solve a constraint satisfaction problem would be to explore this search tree. But actually, this is quite a naive search tree, and exploring it is not really doing anything special. We're actually just doing brute force search, because if you explore this tree, you're actually just going to end up enumerating all assignments and trying them all. However, there are sometimes more clever trees of this form that we could explore. For example, you could potentially make a more clever choice of which variable you want to fix that depends on what you've seen so far. Or you could stop exploring some part of the tree if you find that it already leads to a contradiction. So I won't go into more details, but my point is that there are many algorithms, backtracking algorithms, that work by exploring a tree of this type, looking for a marked leaf. And the starting point for our example will be to fix such a tree. And we're going to use the electric network framework to make a quantum algorithm out of a random walk on this tree. So let's consider subroutines we need for such a random walk, which will also feature in our quantum algorithm. So their complexities will plug into this formula here. First, we need to sample our initial node. And it would be natural for a random walk in this tree to begin at the root of the tree. Remember that in the example of constraint satisfaction, the root of the tree corresponds to having not set any of the variables, and it's the starting point of the classical backtracking algorithm. So our distribution sigma will actually just be the distribution that samples the root, let's call the root R, with probability 1. That's very easy. It's very easy to sort of sample this deterministic vertex. So let's just say that our sampling cost is 1. And to justify neglecting all kinds of costs, for constraint satisfaction problems, we're going to get a cost that's exponential anyway. So whatever the cost of initializing the algorithm to the root is not going to be significant. Next, to update, we need to be able to sample a neighbor of any vertex u. Now, assuming u is some internal node, its neighbors are just the parent, obtained by unassigning the last assigned variable into children, obtained by the 2 possible assignments to the next variable. And I mean, it could be that the selection of the next variable is somehow very complicated, but in practice, this is not usually a significant cost. So I'm also going to say that the update cost is 1. And finally, we need to be able to check if a vertex is marked. And so, for example, in this satisfiability example that I mentioned, then you just need to be able to evaluate the formula if you're at a leaf. And this is also generally an insignificant cost compared to the cost of the full algorithm. So we'll also just call this one. And we're also going to make the simplifying assumption that there's just a single marked leaf. And in that case, a classical algorithm, even one that is deterministically exploring this tree, will, in the worst case, have to explore every vertex. So the complexity will be something like the number of nodes in the tree. Let's call that T. On the other hand, our quantum algorithm will depend on this value C sigma here. And well, I actually didn't define what C sigma is in general, but in this case, since sigma is a distribution supported on a single vertex R, and since we're assuming there's a single marked node, let's call that M. In that case, C sigma is just the commute time from R to M, right? Which is the expected number of steps a walker needs starting from R to reach M and then return to R. Now I'm going to use an upper bound on the commute time, which is just the distance between R and M times the number of edges in the graph. This is always an upper bound on the commute time. And in the case of looking for a satisfying assignment, the path from the root to a marked leaf must be n, the number of variables. And since we're dealing with a tree, the number of edges is basically the number of vertices, which we've been calling t. So we get an algorithm. So we get an upper bound of nt on the commute time, and this gives us an algorithm, quantum algorithm, with complexity square root of nt. So comparing the quantum and classical algorithms, well, we have t versus square root of nt, and in practice, well, t is going to be usually exponential in n, so the square root of n is the kind of term that we've just been ignoring. So really we should compare these as like t versus square root of t, and we're basically getting a quadratic speed up here. Okay, so this was an example in the electric network framework, which was a generalization of the hitting time framework. Finally, I want to give one more framework, which is not going to be a further generalization. It's actually going to be incomparable. And it's based on a different classical algorithm that uses a random walk on a graph. This framework is called the MNRS framework after its authors, one of whom is the instructor of this course. That's the M in MNRS. Here, the simple change that we're going to make to the classical algorithm that is our starting point is that the algorithm is not going to check if the current vertex is marked every single step, but rather it's going to take a bunch of steps and then check, and then take a bunch of steps and then check. And I mean, why would this be better? It could be better if the subroutine we use to check if the current vertex is marked is very slow. So we don't want to run it more often than necessary. In particular, this algorithm takes 1 over delta steps between checking. Here, delta is the spectral gap of P, and it's actually not so important what that means. What's more important is that this number of steps, 1 over delta, is approximately a quantity called the mixing time, which importantly is high enough that after 1 over delta steps, we have a fresh, new, independent sample from the stationary distribution pi. That means that if epsilon is the probability that a sample from pi is marked, then we need only repeat this process 1 over epsilon times, and we can expect to find a marked vertex. Because essentially what we're doing when we repeat 1 over a delta times, updating is we're sampling from pi. So we're just sampling from pi and then checking, and we just need to repeat this 1 over epsilon times. So then, of course, the total complexity of this classical random walk algorithm is given by this expression. And given such a classical algorithm, similar to the hitting time framework, we can compile this into a quantum algorithm with this complexity here, now with 2 square roots, 1 over epsilon and 1 over delta. This framework is the most widely applied of the frameworks, possibly because it never suffered from the drawback I mentioned of not actually finding a marked vertex and only detecting the presence of one. Rather, from the very beginning of the introduction of this framework, it was able to actually find a marked vertex. However, one drawback is that we are restricted to start in the stationary distribution in this framework. And in practice, that could be quite restrictive, as in some cases, sampling from pi might be very hard. But it might be that we can sample from an easier distribution that works just as well for classical heuristics, but in this framework that wouldn't be allowed. Let's compare this to the hitting time framework, where we also restrict to starting in the stationary distribution. Note that the hitting time is between 1 over epsilon and 1 over epsilon delta. So this framework generally does more updates than the hitting time framework, but fewer checks. This could be beneficial in settings where the update is much faster than the check. So let's see one example of such an application. The problem we're going to consider is triangle finding. And in this problem, the input is the adjacency matrix A of a graph, G, and we want to find a triangle in the graph or decide that there isn't one, that the graph is triangle free. And by a triangle, I mean a triple of vertices, U, V, W, that are all pairwise adjacent in the graph. This problem has been an important test bed for the development of quantum algorithmic techniques over the short history of the field. And here we're actually only going to consider the query complexity of the problem, meaning that we will only count the number of times we need to query the adjacency matrix of the graph to find out if there's an edge between two vertices. And we're going to ignore the cost of all other operations. That's going to make the analysis much simpler, but also the algorithm that we're going to show doesn't actually not have particularly good time complexity. Rather, it only has sort of an improvement in query complexity. A classical algorithm for this problem needs to query the whole adjacency matrix, so its query complexity is n squared. But as we'll see, we can do much better with a quantum algorithm. And I'm not going to show you the best known quantum algorithm for this problem, but I'll show one algorithm that is a nice illustration of this technique. So as in our other examples, we first need to specify the graph we're going to walk on. The vertices of the graph that we're walking on, they will be sets of R of the vertices of the input graph, as well as the induced subgraph, which is just the set of edges of G with both endpoints in the set S. So note that the vertices of the graph we're walking on are themselves subgraphs of the input graph, which is naturally a little bit confusing. So let me kind of stress this point. This is one vertex or state of the graph that we're walking on. It consists of a set of R vertices of G and their induced subgraph. So all of the edges in G that have both endpoints in the set. Okay, so then two of these subgraphs will have a walk transition between them if they overlap in all but one vertex. So that means that what our random walk does at every step is it randomly replaces one of the vertices in the set with a new random vertex, and then it finds all of the edges from this vertex to the other vertices in the set. So notice that this is a bit like our element distinctness example where we replace one element in every step, but now there's a bit more structure to contend with. When we replace a vertex, we need to update the subgraph we're storing so that it's still the induced subgraph of the set of vertices, meaning that it includes all the edges in G that have both endpoints in the set. Finally, since we're ultimately looking for a triangle, we're going to say that a vertex is marked if it contains a pair of vertices that are part of a triangle, or equivalently, an edge that's part of a triangle. So for example, if there's some vertex W, not necessarily in the set, that is connected to two endpoints of an edge in our set, and we'll say that, set is marked. So now we get a quantum algorithm with complexity given by this expression here. So to analyze the algorithm, we need to figure out how to fill in these different quantities. First, the probability of sampling a vertex that's marked, meaning it contains a triangle edge. We'll first note that the stationary distribution of this graph is uniform, and that's because it's a regular graph. So if you sample a uniform random set of our vertices, what's the probability that you sample two vertices from the same triangle? Well, assuming the graph has at least one triangle, then there's at least one pair of vertices that are in the same triangle. Actually, there's three, but this doesn't make much difference. So the probability that you sample both of these vertices from a particular triangle is approximately R squared over N squared. Next, the mixing time. So how many steps does it take until you have a fresh random set of R vertices? Well, it's approximately R. And now we have to analyze, we have to say how we're going to implement these subroutines and analyze their query complexities. Remember, we're only caring about the number of queries or the number of times we have to query the adjacency matrix of the graph to ask if there's an edge between some pair of vertices in the input graph. So when we sample our initial set of R vertices, we're going to have to find the induced subgraph, meaning we'll have to query every pair of vertices in the set S to find out if there's an edge between them. And there are about R squared pairs of vertices in the set, so that's the query complexity of the sampling subroutine. Next, when we take a step of the walk, we need to replace a single vertex, and then we add a new vertex. And when we add a new vertex, we need to find out which of the other vertices in the set it's adjacent to. So we're going to have to query, our new vertex with every other vertex in the set. That's approximately R queries. And finally, we come to the checking subroutine, and here things get quite interesting. So we want to implement a subroutine that checks if a vertex is marked, meaning it checks if there exists some vertex W that forms a triangle with two vertices in the current set. And we're actually going to give a quantum algorithm that implements this checking subroutine. So I'm going to go a little bit quickly through this, and I'm not going to give the full details, but basically we want a subroutine that, given some fixed known subgraph, so here we have, this known subgraph, like the induced subgraph here, we already know all of the edges, so we don't need to query them. On the other hand, these vertices are also adjacent to, potentially many vertices outside of the set, but we don't know if we want to learn these edges, we actually have to make queries. We want to give an algorithm with small query complexity that determines if there's a vertex W that's connected to two endpoints of one of these known edges. If you wanted to design a classical algorithm for this task, you might decide to use brute force search to look for such a vertex W. And we're going to do the same, but we're going to speed up the brute force search using amplitude amplification, the first framework that we saw. So first, note that the probability that if there's some vertex W that forms a triangle, the probability we sample it is about 1/n, because there are n vertices in the graph. At least in the worst case, it's 1/n. And okay, next we can easily sample a vertex, and actually this uses 0 queries, and we're only keeping track of queries. So we're going to have this cost set to 0. And finally, how do we check if a particular W forms a triangle with some edge in our subgraph? Well, I'm not going to give the details here, but it turns out that we can implement the checking subroutine of this amplitude amplification step using yet another quantum walk algorithm. So I'm just going to state this as a theorem because I don't have time to go into the details. For any set S, if we have the induced subgraph on S and any fixed vertex W, then we can find out if W forms a triangle with one of the edges in S in R to the 2/3 queries to G, meaning queries to these unknown edges, where R is the size of S. Basically, this theorem just states that the checking cost of our brute force algorithm that searches for a W is R to the 2/3. And I won't prove this theorem, but you'll maybe be interested to know that the algorithm is a quantum walk algorithm, and it's very similar to the element distinctness algorithm we saw in an earlier example. Okay, so now we know epsilon, S, and C. We can fill them in to see that the complexity of our checking algorithm is square root n times R to the 2/3, and this was the final ingredient that we needed to analyze our triangle finding algorithm. So back to triangle finding, we now have everything we need to fill into this expression here. And it turns out the optimal value of R is to set R to be n to the 3/5. And using this value, R n to the 3/5, we can compute all of these costs like so. And notice here that the checking cost is much higher than the update cost. And this is to our, thus it's to our advantage here that the checking cost is only multiplied by 1/square root of epsilon and not by the full hitting time, which might be much larger. So plugging in these values, we get a quantum algorithm with query complexity n to the 13/10, which is significantly better than would be possible classically, since a classical algorithm requires n² queries. And we only analyzed the query complexity of this algorithm, and if we had analyzed the time complexity by counting all operations, not just queries, we would actually find that we get something much worse. In fact, the best known quantum time complexity for this problem is n to the 3/2, obtained by just doing Grover's search over triples of vertices. So you might wonder what's the point of a query upper bound if actually implementing the algorithm would incur much higher cost? Well, as I said, this problem has been an important test bed for algorithmic techniques, and trying to improve the quantum query complexity of triangle finding has led to several new ideas that have had important applications in more practical areas. The problem is actually still open. The best known lower bound for triangle finding is n queries, and the best upper bound is n to the 1.25, which also uses a slightly more complicated quantum walk algorithm. Okay, so that was an example to illustrate how the MNRS framework can be better than the hitting time framework when checking is relatively expensive. So we have the MNRS framework, which uses relatively fewer calls to C, and in fact, this is optimal. So generally the number of calls to the checking operation cannot be improved in general. And then we have the hitting time framework that might use potentially more checks, but uses as few calls as possible to the update subroutine. And we might be tempted to ask if it's possible to have an algorithm that's optimal in both at the same time. And it turns out we can, at least if there's only a single marked vertex. This follows from an algorithmic technique called controlled quantum amplification. But again, this only works when there's a single marked vertex in our graph. Okay, so far we've seen several different frameworks. First, we saw amplitude amplification, also called quantum search. And then our first quantum walk framework, the hitting time framework, which was a generalization of amplitude amplification. And then we allow the algorithm to start in any distribution. We get an even more general framework, the electric network framework. And then the last framework we saw, the MNRS framework, is incomparable to the hitting time and electric network framework. So in some cases, it could be better to use one, and in some cases, the other might be better. But the MNRS framework is also a generalization of the amplitude amplification framework, because when the random walk is on a complete graph, the mixing time 1 over delta is 1, and the update requires us to just sample according to the stationary distribution. So now for the rest of my time, I want to describe a new framework that captures everything that we've seen so far. Controlled quantum amplification is not shown on here. It's actually more general than just a quantum walk search framework, but insofar as it can be used to get a quantum walk search algorithm with an optimal number of both checks and updates, our unified framework also achieves that. Okay, so now to the unified framework. Well, here are our different frameworks, and to unify these, we actually just need to unify framework 2 and framework 3, and that will capture everything. But I'm actually going to explain how to unify framework 1 and framework 3 because it's a little bit simpler and more intuitive, but then we'll see that the technique easily generalizes to framework 2, that is to including like starting from arbitrary distributions as well. So let's see how we can unify framework 1 and framework 3. That is, we'll restrict our attention to starting in the stationary distribution. So consider the MNRS framework. And here we take 1 over delta update steps before checking, whereas the hitting time framework checks at every step. We can easily imagine a classical algorithm that does something intermediate. That is, it checks at every t steps. So it takes t steps and then checks, and then takes t steps and then checks. But if we take t steps where t is less than the mixing time, we don't necessarily have a fresh random sample. So it's not totally clear how many times we need to repeat this t steps and checking loop before we actually find a marked vertex with high probability. But the answer turns out to actually be rather simple. We can just imagine that we have a new random walk, which we'll call p to the t, where we take 1 step of p to the t by taking t steps of p. So if p is the transition matrix, then the transition matrix of p to the t is actually just the matrix p exponentiated to the power of t. Okay, so basically what this means is that the distribution that we get if we start at u and we take t steps according to p, that's going to be how we'll choose the next vertex when we take 1 step of p to the t. So our repeating t times updating, that's actually going to correspond to a single step of p to the t. But now, since this loop is actually just taking 1 step of p to the t, we know how many times we need to do this, just the hitting time of the walk p to the t. By the way, notice here, very importantly, P to the T has the same stationary distribution as P. So the first step doesn't change. And we haven't changed the marked set, so the checking step hasn't changed. Thus, we just get this complexity here. So we have a classical algorithm with this complexity, and we show that we can compile such a classical algorithm for any T. So now T is a free parameter between 1 and 1 over delta, into a quantum algorithm with this complexity, where we have here square roots over both the hitting time of P to the T and also a square root over T, the number of times we update. The key is to show that we can implement the update step of the T-fold walk P to the T in this complexity here with the square root over the T. And to do this, we use a tool called quantum fast forwarding, but I won't talk about the details. So it's clear why this has the hitting time framework as a special case by setting T to be 1, but what about the MNRS framework? In that case, if we set T to be 1 over delta, we just need to show that the hitting time of P to the T is 1 over epsilon. And to see this, recall that 1 over delta is the time it takes to mix, so that we have a fresh independent sample according to pi. So P to the 1 over delta is a process that basically just keeps making independent samples according to pi. And how many times we have to do that before we can expect to find a marked vertex is 1 over epsilon. And so this unifies the MNRS and hitting time frameworks. We get the hitting time framework by setting T to be 1, and the MNRS framework by setting T to be 1 over delta. To more generally merge in the electric network framework, meaning we want to allow to start in any distribution, we basically do the same construction, but we are going to allow the algorithm to start in any distribution. And then instead of the hitting time of P to the T, we're going to get this sort of C sigma quantity, but for the walk P to the T. And so we get a unified framework that has this complexity, where we're free to choose the distribution sigma and also the quantity T. When we set T to be 1, we recover the electric network framework, which has the hitting time framework as a special case when sigma is pi. When we set T to be 1 over delta and sigma to be pi, we recover the MNRS framework. And I didn't mention it, but if we set sigma to be pi and T to be epsilon times the hitting time, it turns out that in the case of one marked vertex, we can also recover this result from controlled quantum amplification, where you have optimal number of updates and checks simultaneously. Okay, so we recover all of these previous things, but notice there are also a lot of other possibilities. For example, we can get something that's like the MNRS framework, except starting from an arbitrary distribution sigma. And the MNRS framework, it's probably the most applied of these frameworks. So it could be used to get to very easily design algorithms like the element distinctness example that I showed, but also some variations of this that are applied to a number of different areas. But it is kind of restrictive to say that we always have to start in exactly the stationary distribution. So if we can start in more general distributions, I think this opens up a lot of new quantum algorithm possibilities. And then of course, there's the parameter T. We're not restricted to set it to be 1 or 1 over delta. You could also set it to be something intermediate. So I want to spend just a couple of minutes talking about why it might be useful to use an intermediate value of T. So first, to illustrate, I want to consider a very structured graph, a torus. And so fix the graph and consider some different possible configurations of the marked vertices. So in two extreme cases, we could have that all the marked vertices are clustered into one block. That's shown in the second graph here. Or we can have that the marked vertices are spread out uniformly, so there's as much distance as possible between them. And just think for a second, which do you think is better for the hitting time framework, where T is 1, and which do you think is better for the MNRS framework, where T is as large as possible? Where T, again, is the number of steps we take before we check if the current vertex is marked. Intuitively, in the first graph here, it makes sense to check as often as possible, because the marked vertices are so spread out. If you aren't checking every time, you'll just walk past a marked vertex and then you won't see it. On the other hand, in the second graph, it might make sense to take a few steps without checking, particularly if checking is expensive. And that's because in this graph, it's hard to find the marked area of the graph because it's so isolated. But once you've found this marked area, you're likely to encounter several marked vertices before leaving again. So it's not necessary that you're checking every single time. And then we can also imagine intermediate cases where, we have the vertices are all in some area, but they're kind of spread out within that area, where you might think that there could be a different good value for t. And in fact, intuitively, there are two aspects to the difficulty of finding a marked vertex. One is that wherever you start in the graph, you're likely to be some distance from any marked area of the graph, and you need to actually travel that distance. But there's no point in checking while you're doing so. And the other difficult aspect is that you also need to get lucky to actually land on a marked vertex. And then you should check every time to make sure you don't miss it. So in the first graph, the vertices are equally spread. So you're actually never that far from one, but when you find it, you better detect it or you're no better off. And in the second graph, or I guess the third graph now, the vertices are all together. So you might need to walk for a while before you hit a marked vertex. But once you do, you'll see more. So no problem if you don't detect it right away. And the parameter t captures the trade-off between these two difficulties, which can vary depending on the graph and the configuration of marked vertices. So for some problems, it should be the case that having an intermediate value of t is useful. And maybe just one more quick example, we could have a complete graph with some number of vertices marked. It doesn't matter which ones. And in this graph, it takes no time at all to mix. The only difficulty is in being lucky enough to actually land on a marked vertex. So you should check every time. There's absolutely no point in taking a step and not checking. Otherwise, you might get lucky, but then miss it if you take a step and don't check. On the other hand, you can imagine a graph where like this, where you have a very large, well-connected, unmarked set, and then a bottleneck to like some marked clique. And in this graph, it's hard to get your walker across this bottleneck into this marked clique. So the walker is going to wander around the unmarked clique for a while, and then eventually get here and then wander around here. So in general, there's no point in checking every time. You need to spend enough time that you get over here, and then when you're here, you'll be marked for a little while. Okay, so that was just some examples of why it might be beneficial to have an intermediate value of t. And I'd like to thank you all again for your attention, and I'd be happy to take some questions at this point.